In this chapter, 1.6 in our book, you will want to review pages 158 through 165. We're going to look at additional types of equations that we're going to try to solve: polynomials, rational equations, radical and quadratic type equations. So our objectives is to look at an example solving a third-degree polynomial. We're going to have an example solving a complex rational equation, a sample of solving a radical equation, and a sample solving a two-radical equation. And then finally, we're going to try to solve a quadratic type equation. We should have seen all of these types of equations in the previous course in 1310. So in our first example, we have the following equation. 12x cubed plus 24x squared is equal to 3x plus 6. The first step is to divide both sides of the equation by 3. The reason we do that is so that we can deal with lower types of numbers. So when we do that, we get 4x cubed plus 8x squared is equal to x plus 2. Now we use the zero principle. We bring everything over to the one side of the equation and set it equal to 0. The reason we do the zero principle is so if we can factor, then in fact we can set up the factors equal to 0 to solve. So when we do that, we get 4x cubed plus 8x squared minus x minus 2 is equal to 0. And we can see we can use the grouping principle to take out an x squared from the two terms, the 4x squared. That leaves us with 4x squared is equal to x plus 2. And then we can take out a negative from both x, negative x, and negative 2, and we get x plus 2. As you now can see, we can factor out an x plus 2 from both terms, and we end up with x to the fourth squared minus 1 is equal to 0. How convenient is that? So now we can factor this into three terms: x plus 2, 2x minus 1, 2x plus 1 is equal to 0. And now we can set each one of these factors to 0. And when we do that, we get the following set of answers. X is equal to a minus 2, x is equal to 1/2, and x is equal to a minus 1/2. So in our next problem, this is number 20 on page 166, we're going to solve the following rational equation. And whenever we have a rational, we need to find the least common denominator. So in this particular case, the least common denominator is c minus 5 times c plus 1. And we notice that c cannot equal 5 and c cannot equal negative 1. So what do? We multiply both sides of the equation by the least common denominator, and that's what we did. Here's the least common denominator on both sides, and we multiply it through the rational equations, or the rational expressions. And when we do that, we get the following: 4 times c plus 1 minus c minus 5. You can see how that works because in the first fraction, the c minus 5's cancel, and I'm left with c plus 1 times 4. And we multiply the second fraction, and we get a minus c minus 5 because the c plus 1's cancel. And over on the other side of the equation, when we multiply that fraction, we just get just the numerator, which is 3c squared plus 3. Now, of course, we use the distributive property, and we get 4c plus 4 minus c plus 5 is equal to 3c squared plus 3. We combine like terms on the left side of the equation, and we get 9 plus 3c is equal to 3c squared plus 3. And now we use the zero principle again. 0 is equal to 3c squared minus 3c minus 6. What we did is we moved everything from the left-hand side of the equation over, and when we do that we have to change the signs. Now we have equal, 0 is equal to c squared minus c minus 2, and now 0 is equal to c plus 1 times c minus 2. Here we did the factoring. We factored the 2. And when we factor the 2, we can set these factors equal to 0. And we see that c is equal to 2, and c is equal to minus 1. But minus 1 doesn't work because when we put it in, we get a 0 on the bottom. And we can't have that situation. Remember, that was our restrictions. And so that's the way we solve a complex rational equation. So we're looking at some radical equations. This is number 33 on page 167. We have the square root of 18 plus 2 is equal to m. We're going to move the 2 over on the other side, so we subtract 2 from both sides, and we get the square root of m plus 18 is equal to m minus 2. It's always good to isolate the square root on one side of the equation. Now, we're going to square both sides of the equation. When we square both sides of the equation, we just get m plus 18 is equal to the square of m minus 2. And now we're going to expand the square on the right side of the equation, so we get m plus 18 is equal to m squared minus 4m plus 4. And we're going to use the zero principle again. We're going to move the variables on the left-hand side over to the right-hand side. That means we would subtract m from both sides, and we get a minus 5m. And we subtract 18 from both sides, and we get a minus 14. So 0 is equal to m squared minus 5m minus 14. It turns out that this thing is factorable to m minus 7 times m plus 2 is equal to 0. And when we set the factors equal to 0, we get m is equal to 7 and m is equal to a minus 2. It turns out in this particular case, m equals 7 only works. The minus 2 does not work in this particular case. So now we're getting into something a little bit more complex. This is number 42 on page 167. Here we have two radicals. And so we've isolated one radical on one side of the equation automatically. That's just the way it works. If we had two radicals on the same side of the equation, we would move one of the radicals over to the other side. So in this case, we have the square root of k minus 2 is equal to the square root of 2k plus 3 minus 2. Guess what we're going to do? We're going to square both sides of the equation. And when we do that, we get k minus 2 on the left side, and we're going to square root of 2k plus 3 minus 2 squared. Now you have to be careful here because you have to FOIL the right side of the equation out. When you do that, and I'd like you to do this on your own to FOIL to see if you get this answer, you get k minus 2 on the left side is equal to 2k plus 3 minus 4 square root of 2k plus 3 plus 4. Now, of course, we want to combine some like terms on the right side of the equation, so we still get k minus 2 is equal to 2k plus 7 minus 4 times the square root of 2k plus 3. Now, we want to isolate the square root on one side of the equation, whatever we have left, and we do. So on the left side of the equation, it's going to be a minus k minus 9 when we move the 2k plus 7 to the left side of the equation. And on the right side, we get a minus 4 square root of 2k plus 3. Now, we divide through by a negative number, and we get k plus 9 on one side of the equation, and we get 4 square root of 2k plus 3. Now we're going to square both sides of the equation. And when we square both sides of the equation, we get the expansion up here of k squared plus 18k plus 81 is equal to 16 parentheses 2k plus 3. Now, again, we're going to use the distributive property on the right side of the equation. And when we do that, on the left side stays the same. K squared plus 18k plus 81 is equal to 32k plus 48. And now we want to use the zero principle, so we're going to move those items that are on the right over to the left. So we have to subtract a negative 32k from both sides of the equation and a negative 48 from both sides of the equation. And we end up with k squared minus 14k plus 33 is equal to 0. It turns out that is factorable into two pieces. K minus 11 times k minus 3 equals 0. We set those factors equal to 0, and we get k is equal to 11 and k is equal to 3. Well, at this point, it's important to put these back into the original equation to see if they work. And you should do this on your own to make sure that they work, to check it out. I've done that, and they do both check out. The last equation we're going to look at is number 60 on page 167. Here we're trying to solve a quadratic type of equation. And what we mean by that is that there looks like there's a square term and a single term in the equation. So in this case, you can see that the square term looks like this, and the single term looks like this. And so what we're going to do is we're going to let x equal d over 1/3, right? So now, when we do that, we're using a substitution method, which is used a lot in mathematics. So when we do that, we now get 3x squared minus x minus 4 equals 0. Oh, that makes things a lot easier, because now we know we can factor this equation into 3x minus 4 times x plus 1 is equal to 0. We can set the factors equal to 0. 3x minus 4 equals 0. We end up with x is 4/3. Now we have to substitute back in. You know, we solve for x, but x isn't what we're trying to solve for. We're trying to solve for d. So now d is 1/3. D to the 1/3 is equal to 4/3, and we do what? We cube both sides of the equation, and we get d is equal to 64 over 27. We do the same thing with x plus 1 is equal to 0. X equals a negative 1. Now we cube both sides of the equation because we set d to the 1/3 power is equal to a -1, and we get d is equal to a -1. So our solution set is d is equal to 64/27, and d is equal to a -1. Both of them seem to work. Well, that concludes Chapter 1.6. Please look through some of the problems in the chapter and see if you can do them. And we will start the next chapter 1-8.